Fourier transform work. And if something is of this form in the Fourier domain, okay, what it means is that these are phasors now. If I were to think of this in the Fourier domain, then in the time domain, then this should be convolving with this, right? This will be convolution. And if this is independent of frequency, this becomes a delta function in the time domain, like this would be, okay, and this would just reduce to epsilon naught Et. If this is independent of frequency, this is for vacuum. Okay? So which means that if this is a delta function, it means that whenever you apply an E, you instantaneously give rise to a D, instantaneous response. However, if this is a function of frequency, it means that there will be some relaxation, there will be some delay due to convolution. Whenever you apply an E, it has to relax through the system through a convolution before you give an D. Okay? And all material media are made of molecules and atoms. And you can think of carbon, the D as coming from the vacuum part plus a polarization part. The polarization part can be due to dipole moments or atoms in the system that have inertia. They cannot be instantaneously moved. This part cannot be instantaneously changed. If you want to polarize the molecule and atom, it takes a finite amount of time because they have inertia. Okay. And all material media will have to have this kind of behavior to obey the law of physics or to obey Newton's law that they have inertia. Only vacuum can behave in this manner. Okay. So that's the frequency dispersive media. And all material media have to be of that way. And then of course you have to have the spatially dispersive media. Then epsilon is a function of k. Mu can be a function of k, for instance, or maybe even the k vector. In that case, what it means is that in the spatial domain, B of R would be epsilon of R convolving with, in the spatial variable, E of R. Okay, so if you take this to the Fourier space by Fourier transforming in space, then this becomes B of K is equal to epsilon of K times E of K. Okay. In order to get this relationship, we have to do a further Fourier transform in space. We go from here. Spatial Fourier transform. Okay. So those are the meaning of a spatially dispersive medium. You can have nonlinearity too. If epsilon is a function of E or H. Okay, then mu is a function of E or H. Then you have nonlinear medium. And this is often seen in plasmas and optics. Okay, this kind of material is quite common. So nonlinear optics is a big field because this kind of phenomenon is quite often observed. Okay? Are there any questions so far? So the next thing I'd like to talk about is actually Poynting theorem. Poynting theorem and energy conservation. You probably have learned that in your undergraduate courses that if I have E of RT and H of RT, and if this is a time harmonic, then they have their corresponding phasor representation, E of R and then H of R. Okay, these are the phasor representation of this. And you can think of this as the Fourier transform representation of this for a fixed frequency. And you can prove that this quantity, which is this quantity over here, take this and plug it in there. Okay, and take the time average. The time average is defined to be limit of t going to infinity, 1 over t, 0 to t, of this quantity, E of R t plus H of R t dt. Okay, this quantity is of interest because electric field has a dimension of volts per meter. Magnetic field has a dimension of amperes per meter. So if you multiply these things up, this has a dimension of volts times amperes per meter squared, or watts per meter squared. Okay. So this is a kind of a power density. It's a kind of a power density. And you can prove that if this is a time harmonic signal, and that if E of RT is given to be the real part of E of R, e to the minus I omega t. If this is the case, you can show that this quantity here can be written as the half the real part of the phasor representation crossed with the H, the phasor representation, taking the complex quantity. Okay, I guess all of you know this, right? If you want me to prove this, I can prove this for you. But presume that all of you know this. All of you know this relationship, right? And this relationship follows from circuit theory. You might have first seen it in your circuit theory course, that if I have a time harmonic current time, I of t, and then a time harmonic voltage as a function of t, and then find the phasor representation I tilde, B tilde, then the power BIT. Okay, this is time harmonic, and then take this time average of this quantity. It's going to be half the real part of BI tilde. Okay, this is something that you might have learned in circuit theory. And might be first proved to you in circuit theory. And if you repeat this proof for this one, you will get exactly this relationship. Okay? I hope I don't have to prove that to you. But once we prove energy conservation and prove that this quantity is conserved. Okay, this quantity is somewhat conserved. So let me take the divergence of this quantity. And actually, I will be tempting to put a tilde over here. Okay, we're going to take a break soon. Okay, just give me a few more minutes. Okay, I'm going to prove that this quantity is conserved. And it is conserved by Poynting theorem. And I guess you have seen this proof before. You have seen this proof before in the undergraduate courses, right? So I'm going to do a different proof for graduate courses. Okay, so that you see a slightly more complicated version of this proof. Okay, maybe I can take a 5 minutes break and then you can come back and look at the proof for this pointing theorem. Okay.